Right. Again, hey, good morning, and thank you again for hosting me here, Yaroslav, and all the organizers of the summer school. I landed in Krakow around 4 p.m., and we were optimistic that we'll maybe get here by 9 p.m. That didn't happen. The border crossing took much longer than we thought it would, and we got here at midnight, then woke up at 6 a.m. to some silence, and I wasn't sure what to do. Uh, and then I said, all right, maybe I should go down. Then the silence stopped. And then the silence started again. And then I texted Yaroslav. He's like, the second one is mean it's safe. The first one, you had to go down. I'm like, oh, now I know that it's not a test. You just have to follow it. But again, thank you all so much and for getting together here today. And I do realize that I'm leaving tomorrow. It's a short trip, but already what I've experienced, I'd love to be able to come back again and spend more time with all of you here. So what we're going to talk about in the couple of lectures that or the things that we have that I'll be presenting on, we would focus on the idea of sort of graph representation learning, how we got there, what we are doing in my lab, uh, and motivating why we look at the world and the complex systems as a graph. And then what are some of the complexities that come with it, and how in the last, literally in the 6, 7 years, this field has transformed, right? Where we were originally doing graph representation learning in a very typical network science-based approach. Then we moved on to more random walks and then graph neural networks. And then now we are moving on to different challenges. And this is sort of the beauty of machine learning AI today. It's fast moving, the amount of research that's being produced, the amount of work that's been done. So I do, folks who are in this summer school, as you're thinking about your research or things, be impatient, be curious and impatient at the same time, because there's some really interesting problems to be solved. And at the same time, the science is moving quickly around this, and which is great. And then as well as we may not have a chance to talk about it today, maybe next time when I come, and Yaroslav, and he visited us on Notre Dame, we had this talk about how do we sort of create a Lucifying what we are doing at the Lucy Family Institute, as he introduced earlier. We are driven by one thing, that there are some significant societal challenges that need to be addressed, whether, and how do we contextualize them to the country, to the society, to the community, to the city, to the county that we live in, whether it's in poverty or climate or energy or healthcare. Pick one. And as you then start thinking about what kind of data we need, what kind of modeling we need, what kind of AI we need to solve, and then also think about how do we translate those. Let me tell you one thing, the easiest thing is of this entire journey is actually developing the algorithm, doing deep graph learning or developing the AI model. The second hard thing is that's the easiest thing. The second easy thing is identifying data, getting data. Finding partners. The most difficult thing is the translation of the work that we do to demonstrate it could actually be translated as a last mile challenge into something that your partners, stakeholders, society can absorb. And that that is hard. That is the hardest part of this equation. And that's why I would hopefully, I'd encourage all of you to think about is that impact of your work that's realized through maybe one life is benefited, maybe 10 lives are benefited, maybe something positive happens from an infrastructure standpoint or healthcare standpoint or climate or environmental aspects, ag aspect, there's significant agriculture that happens here. So whatever that may be, so sort of even think about those partnerships with stakeholders that go beyond the technical work we would discuss, because I think the society needs more of this than what we do. All right. So having said that, so this is sort of we would touch upon. My goal here is to feed in some ideas and sort of set some introduction, build intuition around some of these concepts. There's enough research papers out there. There's books, there's our papers that you can read and get deeper into. But I'd like to use these couple of lectures to get more of an intuitive understanding of what do we do with graph representation learning? What are some of the challenges? How do we sort of address some of the, what is graph few-shot learning, and what are some of the applications, etc. So we will go through that a bit more. But before we go ahead with that, by show of hands, how many of you are already doing graph representation learning in this room? Lovely, that's awesome. Even if you are, don't raise your hand, right? Because then I'll feel like whatever you know, I taught you. Just make me feel good. I'm just uh, but and then how many of you are, if not doing graph representation learning, are doing something with large language models? As a user, you're actually developing, modeling, fine-tuning them. All of the above. But so using them. So custom using the API for custom applications. Is that what you said? All right. And how many of you have actually, gone through, I guess this is the summer school of data science, data science, AI, it's all the same in my opinion, right? It's just, we go with whatever is selling today. Once upon a time, big data was the thing. Then data science became the sexiest profession, according to Harvard Business Review. Now it's AI, then it's generative AI. Who knows what it would be tomorrow? So let's to me, it's all machine learning, essentially what we're doing here, what we're talking about. That's being true to what we do here. So how many of you feel really confident about machine learning or AI concepts per se? Everyone? Have done introductory ML, AI? Yeah? Cool. All right. All right, cool. So now let's think about graphs, and why I'm fascinated by graphs is, so when I did my PhD, I finished my graduate, did my PhD in 2002. Then I went into banking for a few years before I became an academic. And, I'm a traditional fundamental machine learning kind of guy where, we did work on learning from imbalanced data. I developed this algorithm called SMOTE. I don't know if you all have used it for imbalanced data. I created this field of imbalanced data learning through my research. And, that paper is extremely, extremely highly cited. Every software package has it and every textbook. And if you're doing anything in imbalanced data, you must have used SMOTE one way or the other. Every software package has it today. But then as I started my academic career at Notre Dame as a professor in 2007, I started thinking about graphs and networks. As we looked at complex systems, as I was even leaving the financial industry, there are transactions that happen. If you think about transportation, there are networks, right? If you think about social networks, social media, it's a network. We are connected to each other. Any complex system that you may look at, even if you look at chemistry, a human anatomy, we are connected, the gene networks, the protein-protein interaction networks. These are graphs. At the end of the day, how we represent the data is important, but can we maintain the connectivity of that complex system that already exists as a graph? Right? If you think about your power grid, it's a graph. Airport transportation system, there are hubs, big airports, and there are things that can get connected. Amsterdam is a hub. Then folks go on small scale and city hoppers to other places from Amsterdam. But Amsterdam is the hub, right? So there, it's a network. Train stations are the same thing, right? So you can start thinking about these complex systems in the world as they are nodes, and social networks, are connected to each other. They are nodes and things are connected. Chemistry is an application area that we are really invested into. In fact, the reason I could only come here for a day was I spent one day for the National Science Foundation workshop at University of Minnesota yesterday. Today's what, August 8th? I forgot. Today's 8th, right? On August 6th. I left on August 6th, the US. So August 6th, I spent the day there and we were talking about AI for science, AI for chemistry. That's going to be revolutionary. Yeah? And especially given the size of UCU, the size of this university, if there's something that you need to build on, is capitalizing on the interdisciplinary connections you can make. This is just a perfect size, perfect, location, co-location of individuals that you can really tap into interdisciplinarity. And if you think about AI for science and chemistry and chemical reactions, there's some amazing opportunities there. But even if you look at chemistry, those bonds, and we got a big $20 million NSF grant for that, US dollar, wherein, the atoms, and that's a molecular structure, but it's a graph. It's in 3 dimensions though, because we have orbitals and things, but it's not a 2-dimensional footprint. Not, you know, everything that we are talking about is in multiple dimensions. There's space, time with that. So as we start thinking about these graphs, then the question becomes is the data that we may get, whether it's chemical reaction data or the social media, Facebook, Twitter, now I should call it X, or Snapchat, or whatever social media you may be using here, that data is not, when you extract the data doesn't say, hey, this is the graph, take me. You have to collect the data, you have to figure out what are the connections and build a data structure that is capable of treating that as a graph, right? And there's multiple of such things available. And then, you know, you have to start thinking about what all is part of the social network, right? Is it only the network structure, or are there attributes that are attached to this network that we've extracted? So for example, if you think about your Facebook network, you may get your friendship network out of it, but then you may say, oh, but there's content about me. There's a personal profile information. That's not just network. There's also things I post. I may post images. I may post text. So there's a lot of multiple modalities of this data. So those are some of the other challenges we have to think about, and we'll go through that process as well as to how we tackle this in my lab. And then once we sort of have this graph available, right, we could do multiple things. We could do node classification. We could say, okay, can I classify this node with certain properties, with certain attributes, with certain annotation? Can I predict a link, whether this link will form between two individuals or not? And that's a hard problem. If there's billions of nodes in Facebook, how does Facebook recommend to you what individual you should be friends with, right? It's a tough one to tackle, right? So how does Facebook sort of address that link prediction challenge for you? This graph classification challenge, can I sort of label this subgraph or a graph and say that this subgraph has this property or has this reaction, has this capability? And then I can do clustering as well. So there's many things that machine learning can do. So as I said to you earlier, the challenge number one is getting the data, taking a look at the complex system that you're tackling. Even if you say, look at Lviv and city infrastructure, what have you, you may say, okay, what kind of problems, real world problems I want to tackle? And is it a complex system? Is it a complex system that has different components to it, different nodes to it? Is it a complex system that has connectivity to it? Yes, then I can maybe get the data and extract a graph out of it. That's a step one. What's my problem statement? Then you have to ask your problem statement, am I now doing classification at the node level or even regression? Am I predicting which two nodes should be connected to each other but are not connected as yet? Am I doing graph level classification prediction or something else, right? So those are the kinds of things that we would begin to address here. And then as well as there's many other things that, you know, folks are doing, and other applications include in NLP, whether can I predict what news articles and subjects that, you know, can I do fake news detection? Can I do a scene graph generation? So a lot of this generative AI is also looking at these graph-based principles, wherein if I describe, I need a man, a rider who's riding a horse, there's a mountain behind, or there's trees behind on the field. I can do those descriptions and I can build a connection as to what kind of descriptions are available. And then maybe I can create an image or go from an image to a graph. And I can do program analysis, as if you look at the programs that we write, they're function calls. You call a function that calls something else, that returns me something else. It may have a recursion to it. So these are all connections, if you will. So how do we sort of begin to address some of those things as well? So when I first started working in this area of, you know, in graphs, as I said, I was more imbalanced data learning person, traditional machine learning person. And then as graphs, machine learning and networks and these real world challenges came about, and we started looking as, now most of the work we do is as graphs. We still do work in imbalance, but most of the students who are doing this work are on the graph side. When we, you know, our first paper was in 2009, 2010, where we came up with a new link prediction algorithm. And the way we would sort of go about doing it at that time was, I'll take a graph, I will compute features on that graph, right? And when I say I, the students, I shouldn't say I didn't do any work. The students did all the work. I get to come to beautiful Lviv and present the work they did, but it's their work that I'm talking about here. So we took the input graph, we looked at the nodes and we looked at the properties and the characteristics, whether it's a degree, preferential attachment, clustering coefficient, every statistic, every characteristic that we could calculate about that graph or the network, we did that. Right. So once we did that, we said, okay, now those become structured features, and then we did learning algorithm and we did prediction. The challenge with all of this is, as in any machine learning application that you're working with, is it requires the feature engineering piece, feature generation piece is almost like a wrapper. You must know what the downstream task is, and then you go back, you extract the features that you need for the downstream task, and then you sort of solve for that, and then you do the classification. Then you do, okay, now this is looking good. We can proceed with it. And then you come back if you have to do some other downstream task, etc. So there's lots of these caveats that go with these kind of features of graphs, and uh, learning algorithm. It can be very time consuming, but we did well. So then what we were sort of the notion of graph representation learning in 2016, 17, it's again fairly young in terms of a research space, right? That, 7, 8 years is a young field. But a lot has happened in these 7, 8 years. The papers we published have a few thousand citations in 7, 8 years on this topic, right? So the idea of the graph machine learning was that, hey, could we, as we were thinking about representations, what is representation learning? A representation learning simply says, give me your data, give me the structure, and I will try to vectorize it. At the end of the day, what does a learning algorithm need? Who wants to answer that? A feature vector. Thank you. Right? It doesn't care whether it was text or image. Does it care? You have to vectorize that, right? It needs a feature vector. So every time the question that you're asking of yourself is, how do I take what I have? Even if I were to say, okay, let's collect the data about this room. We can do dimensions of the table, the chairs, the number of people. We can have our attributes attached. That's great. But then I have to put it together as a feature vector as an X. And my Y could be a label that says, it's a podium, it's a desk, it's a chair, it's a round table, what have you. And then I can have classification, but I need to give it that XY. That's the sort of the feature engineering. So could we, and given that, how we were doing feature engineering on graph by calculating all of those characteristics, features, and properties of the graph, it was challenging, right? Could we automate this process such that we can create a real valued representation, essentially an embedding, right? So that was the idea. That was the intuition that folks like in my lab and Yuri Leskovich's lab at Stanford, as well as in New York, there are 3 groups that started looking at this problem. It so happened simultaneously, and we all tackled the solution in a very different way. So we published papers one after the other. In fact, my dad, the student who did Aditya, who did the first work on on graph vectorization, received the KDD's our main the top data science conferences in Barcelona in a few weeks. If you're not, I encourage you to go, not because it's in Barcelona, it's because it's a great conference. But then as well as we had my student received the same KDD outstanding dissertation runner-up in 2 years later for the same tackling this representation learning problem. So this is what we are trying to get to at the end of the day, right? In the initial works that we were doing, our question was, can I learn features from a graph that looks like this and get to X, which is my embedding layer, and then use it for arbitrary learning and mining tasks? That was my latent representation matrix that I had to learn. The question was, how do we get there? Just around that time, how many of us are familiar with Word2Vec? Awesome, right? Awesome. Quite a few of you. So Word2Vec came about, which basically said, hey, I can take a sentence. Before that, topic modeling was doing more latent Dirichlet allocation, LDA-based models, etc. Word2Vec revolutionized that, right? It said, I can give me any arbitrary sentence, and I will create a latent representation vector from text. So if I give you these words, it would say, okay, it looked at the proximity of words. We'll take every word and say what other words are next to each other. We'll do some encoding based on that and feed it to a neural network and get the first hidden layer. That's the embedding, that's the encoding, and do squashing on it. So everything is between 0 and 1. Now it's learnable and take it from there. So we were able to do that for words using Word2Vec, right? Essentially, it said, if words occur closely together, then there's a context that they represent by occurring together. I mean, even if you think about large language models today, the generative AI, they are essentially, probabilistically predicting the next word based on what they have seen before. They don't have an understanding of what they have. It feels like they understand when you're talking, but they are simply taking your question, projecting it to the embedding space, and boom, 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 probabilistically generating the complete sentence. And that's why the answer you get for the same query is different, because it's probabilistic. It is nothing deterministic with them, right? So they're building up a sequence of those as they go along. So this had happened with NLP board. So then the question was, can we apply those concepts to a graph like this? Right? Could I sort of use the notion of Word2Vec and see what can I do to get to my latent representation vector? Where now, instead of text that looks like this, I have a graph that looks like this. So what we could do, if we imagine the graph is representing a language, right? It doesn't matter what language it is. It's a language for even Word2Vec. It doesn't matter what language Word2Vec is being learned on, whether it's English or Ukrainian or Polish. It doesn't matter, or any other Slavic language. It doesn't matter, right? It's what words are occurring. It's tokenizing those. So if we think about this thing as graph, and we look at the nodes are representing that language and how they're connecting, what if the nodes and their connections with each other are indicative of my location and proximity of words? What if these nodes are words in the language of the graph? Are you guys are you with me? Right? Arguably, that intuition can apply, that these nodes are words and the graph is a language. But the nodes are not coming as sentences, right? In the previous diagram, in the previous figure, I'm sorry, I had imagine these words, but those words are my graph, but they come together as sentences, right? I don't have sentences though, but I have a collection of words that come together. So what if now I do random walk on my graph? I can only randomly walk from one node to the other node if it's connected. What if I do multiple of these random walks? Now I have created sentences, if you will, right? I've created things that go well together. And if certain nodes happen together in many different random walks, then maybe those nodes have a higher probability of occurring with are co-located with different kinds of nodes in the graph. So I could then do that. And now I can simply say, hey, I have sentences and I have Word2Vec that exists. I can just learn an embedding. Yes. So you actually, so when you that's a great question. So you actually you introduce constraints within your random walk. So you can actually, it's a directed random walk where you're essentially saying if there's a loop, you ignore it and you skip. If you don't need to ignore, then you can specify that. So if you don't need to ignore, then if you're finding yourself in the cycle, then because you don't need to ignore it, so you'll find yourself in that cycle, right? So that's of course the challenge with any. So you are basically, how you random walk is up to you. There's many different ways of doing a random walk. right? You can make it more deterministic, you can make it more probabilistic, and you can even make it that, hey, after a certain point you have to skip out of it, right? So you can introduce those constraints to your random walk. But good point. So, but then that's it. Folks have figured out, struggled with exactly that issue even when building out this. So there are heuristics that have been introduced, including the heuristics that we have introduced in our work. But that's a very good observation. So then once we have this, we can sort of use the same theory as the word2vec and build a latent representation vector. Great. So is the intuition clear? And then once we have that, then we can do the same encoding, one-hot encoding, or etc., to sort of do a placement of each node and then get the first hidden layer out. That becomes my embedding, and hence, 128 dimensions, 64 dimensions, 256 dimensions, they are largely coming from that, the hidden layer, the embedding layer that we have from a neural network. And then we do a squashing function of that, so we can get it between 0 and 1, and voila, you have your feature vector that can be used for any downstream task, because it's simply X. It's unsupervised discovery of features. What we were doing before, when we were identifying, manually doing feature engineering, they were driven by the underlying tasks that we had. Be good? All right. However, so that was great, right? So that sort of tackled the problem for homogeneous network. But the challenge that uh, we wanted to solve was the challenge of heterogeneous network. So it makes sense, like, the previous graph so far, that the structure that I've shared with you is of homogeneous graphs where all nodes and edges are similar to each other. All right. But now the reality is almost every graph is heterogeneous. If you think about um, a citation graph, or even if you think about your social network graph, right? One would say, okay, I'm connected, but their attributes, is this a family member? Is this a friend? Is this a colleague? Is this a professional connection? They are descriptors to the relationships, to the links that we share. And those descriptions are important, right? It could also be that my attributes, my profile information, that's also heterogeneity. It could also be different kinds of nodes. Let's say that within your social network, you have a place node where it says, I am connected to Yuku because I work here or I study here. Well, now even I am connected to Yuku as a node. If Yuku was a node, if this university was a node, right, that's a place node, right? So imagine if we all were to build a network with each other. Yuku would be a common node now amongst us, right? And then some of you will share some different relationships or different connections, and you may even do a project together. That will be a different connection, etc. So there's heterogeneity in all of these graphs. And whether it's user location or publication, co-author, there's many different kinds of relationships that could happen. Even if I'm on Amazon, the products are connected to each other. I am connected to the products, etc. And everything is heterogeneous. Then the question becomes, if you have this kind of heterogeneity in a graph, how do you do representation learning? Essentially, what we are saying is, what if I give you text, which is mixed language, Ukrainian, English, all put together, and Polish? Choose, take 3 languages in one sentence. That'll be interesting, right? But that's the heterogeneity. How do you now identify the context? The context is of each word. It's difficult, right? How do you sort of get that? And that's the same thing we have here with these heterogeneous graphs, is that how do we now identify the context of these things? All right. So this is where we started with. This was the work that was we published in KDD in 2017, and this led to my student Yuzhao Dong receiving the second best dissertation award, and he's a rising star of data science award and things like that. This paper is laid the foundation for representation learning. This is the first work to be done on representation learning on heterogeneous graphs in the literature in 2017. And since then, that field has blown up significantly. So we sort of said, okay, what if we start with a graph that looks like this? This is an academic publication graph, and we have, imagine that you have an author that is working at an organization. So we have here an example of, say, MIT and CMU, and there are authors that work at those organizations. There's an organization node, there's an author node, and P is a paper node, what paper we wrote. And then finally is the venue node where we published it, ACL or KDD, etc. So now imagine that this is the graph, which basically two authors could be connected to each other because they collaborate. Two authors could be connected to each other because they work at the same organization. Two authors could be connected, two papers could be connected to each other because they cite each other, or one of them cites the other. So there's a directionality. And the authors could also be connected if the papers were published in the same venue, ACL or KDD, etc. So you can imagine the different ways the connections and among the nodes could happen. And then the question is, if I give you a graph like this was a challenge that I presented to you, Jar, as well, that what we were working with is that what if we do a graph like this? How do we now do random walks on these graphs? It's complex, right? Because there's different node types, different relationships. Like, what are we trying to get here? How do we get the pattern out such that we can get to the latent representation vector? So this was sort of the two challenges that, the two questions that global research is, how do we effectively preserve the concept of node context among multiple types of nodes, authors, papers, venues, etc.? And can we directly apply homogeneous network embedding to heterogeneous networks? The other thing was, what if I take my heterogeneous graph and I break it into multiple homogeneous graphs? I can say I'll only do an author graph. I'll only do a paper graph. I'll only do a venue graph. What if I do those? Does that solve my problem? The answer is it doesn't. It doesn't perform as well. So but we had to evaluate that so we could convince the reviewers that this was the more plausible way of approaching these challenges. So we developed this method called MetaPath2Vec. And what we did is sort of, this is the overall architecture of that. We call it MetaPath2Vec because we said, okay, to answer to the question that he had asked me earlier about what happens with recursions and things like that, right? So we sort of said, we gave schema, we gave kinds of paths we wanted the random walker to go through. So we said that, hey, I need you to do a path that only goes from author to paper to author. If you're a random walker, you start from author and an org comes, skip it. Only move forward if it's a next node is a paper node. Then only move back from there if the next node is an author node. And as long as it's a different author, don't come back to me. All right, so we wanted to avoid the inversion problem there. And then we had author, paper, venue, paper, author, and then organization, author, paper, venue, paper, author, organization. Right? So we suggest these are just examples. We had many different kinds of meta paths, but so you sort of gave a directional idea to the random walker to say, these are the kinds of sentences I want you to discover. Okay. And then we said we will build a skipgram model, which is typical what you do. And we could get the encoding layer, embedding layer, and life is good. And so sort of the way we went about this was we defined a metapath-based scheme, right? And we also defined the recursive guidance for random walkers, as I was sharing with you earlier. We described it. We said what kind of paths we need you to follow. And then we were able to compute the transition probability at each step. And we also gave the recursive guidance that, okay, do you need to, if you're coming back to that node, what kind of conditional probabilities you need to achieve to be able to follow that recursive guidance, if you will. So we were able to now create a random walk paradigm using these metapaths. So that sort of is what we described within the paper, that this is now a So this was the key contribution was we said, okay, we can describe these metapaths, but how do we construct random walks that captures the intent of the metapaths that we have given? And so one challenge with the skipgram here was that we could, as you notice here, the output layer that what we are interested in, remember these are encoding multiple shot encodings, right? Author node, that's where you only see author as one. The reason is one shot is that only one is highlighted and everybody else is zero, and you do it for every single input vector this way. Is that probability that KDD appears as a conference, which is the output node here that we are interested in, that if the author is publishing at a venue, which is the output, we are trying to compute that probability of KDD appearing across all kinds of nodes. There are different kinds of nodes. There's an organization node, there's a paper node, there's an author node. But then what we are saying is that we'll compute the probability of a conference occurring, a venue occurring across the different kinds. That's not quite good because I am now computing a probability of, say, this roundtable occurring across every kinds of things versus I should be more calculating that this particular kind of roundtable, a small roundtable occurring across all kinds of roundtables only, right? To give me a sense of what's the likelihood of KDD as a venue, KDD as a conference occurring across this author collaboration network with respect to the other conferences, not with respect to everything else that's in my data. I'm interested in that. So we had to get the context. So what we sort of did was we developed a heterogeneous skipgram model as well. And again, the details and the math behind this is in the paper where we looked at what's the probability that the venue occurs from the context of all venues, what's the probability that the author occurs from the context of all authors, what's the probability that the organization occurs from the context of all the organizations. And then we sort of built our skipgram layer from that perspective. And this was the overall, calculation. And, who would explain why do we do softmax with these things? Yes. And within what range? 0 to 1, right? To get, it's a squashing function, right? We do softmax, we could do that. And we always need an objective function for sampling as well, because remember, there's lots of different sampling we could do. We are more interested in negative sampling. We have to do negative sampling, and then we do a stochastic gradient descent to solve for this. And the difference between metapath to vec and metapath to vec plus plus, remember, this method we are calling plus plus, and the other one we didn't have plus plus to it. We were not very creative with naming. We said one is metapath, the other is metapath to vec plus plus, just because why give it something different? This is computed for the context. See the differences? It's computed for the context. The sampling is done from that context. All right. So those were some of the key differences that we did. And then, it was, of course, and this really solved the problem of heterogeneous graphs from a structural, things like that. Let me just, all right. Then, by the way, any questions before I move on to the next piece of graph neural networks? Anything else so far? Any other questions on the embedding methods that we've talked about? So you get an input graph, right? You're basically the random walker. You're sort of specifying is that this is, you're giving a recursive guidance. You're telling the random walker when to stop. You're introducing a stopping condition. You're telling it how to calculate the transition steps based on the probabilities. That's what the random walker is doing. And you're saying randomly pick a node and go this far, right? So like, for example, with graph neural network, as I said, you're specifying whether it's one hop or two hop. You're similarly specifying how far you want a random walker to go. If it's a billion node graph, you don't want the random walker to go to millions of nodes and, it's going to be too complex. So you need to introduce how far you want it to go, right? So that's what so you pick a node at random, and then probabilistically it's going to calculate the transition to the next one and make sure that it's not going back and circling with itself. So that's what then. So no, you need multiple. You need tons of those, right? Because what you're trying to do is you're trying to understand as well with these random walks is, let's say we do a random walk amongst us, and of all the, if I take all your social network, right? Ideally, if there's one or two or few of you who's more connected to others, if I'm doing the random walk, I hope that, so let's say if you are amazingly connected to everyone in the social network, let's say you're Mr. Popular, all right? And you should then for me to say you are Mr. Popular, or the data to say that, if I'm doing multiple random walks, you always come in different random walks, right? How do we extract that proximity information? So there's, I don't even remember how many random walks we did, but we tried to get as much coverage. And that's where the notion of negative sampling also comes in. As much coverage as we can in making sure that we are doing as many nodes we can select, in making sure that we're doing random walks that capture the neighborhood of the properties of my graph. And the other thing that we also have to make sure is that a few of us may be connected, may have very high degrees of connectivity. I don't want the random walk to simply be influenced by those. Right? So I have to be able to jump over to other parts of my graph to begin random walk over there. Right? So there's a lot of heuristics that go into random walk. And this is what graph neural networks overcome. We'll talk about those two. Anything else? Good questions. Yes. So the main goal, that's a good. So with the MetaPath to WEC++, what we actually solve with them is, so if you sort of look at this here, right? MetaPath to WEC. My output layer. So remember, I'm doing this encoding and I'm getting the output and I'm getting a probability where I'll be doing as you said, I'm going to be doing a softmax function here. At the end, I would say, okay, probability that a node, say, called KDD occurs, okay? And I'm going to compute the typical skipgram is I'll compute that probability of KDD occurring as a conference across all types of nodes. So I'll calculate the probability of KDD over papers, over authors, over organizations, right? So that's not giving me a complete picture of what's the likelihood of KDD occurring as compared to the other conference venues. It's the likelihood of KDD occurring across all kinds of nodes in my graph. So the probability is calculated across the entire graph, which makes sense for homogeneous graphs because all nodes are the same type. In heterogeneous graphs, all nodes are not the same type. Okay, so now to overcome this, we do this. We do the plus plus is the heterogeneous skip graph. Okay, so now we are saying probability that KDD occurs is only calculated across the node type venue, all the conference venues, conference places. Probability that author occurs is calculated across only the author type nodes. Probability that an organization occurs is only calculated across the organization nodes. Probability that a paper occurs is only calculated across the paper nodes. So this becomes a heterogeneous skip graph, which is not typically done, which is not, so this was a contribution because skipgrams are not done this way. So we had to change the math to capture the skipgram, where now we are computing the summation of this only of a particular type of a node versus this. So this was a difference between the way the softmax was done and the way the sampling was done as well. Sounds good? Oh, sorry, KDD is a conference. It's a venue. ACL is a conference. It's a venue. So where you're publishing the paper, it's a venue. All right. Sorry. I just assumed that everyone is coming from the same field. We know all the, I should be more clear. Thank you. Thank you. All right. So now, so one thing which is amazing is what your questions have shown me is you are thinking about the limitations of this, right? How many random walks should I do? What about those darn cycles and loops? When do I stop? Right? This skip gram. Why do we need this heterogeneity and things like that? The graph neural networks then happened around 20, became popular again, 3, 4, 5 years ago. And now they've become a pretty big deal as well. And, I also was not really excited about the idea of using these shallow node-based embedding methods. When I call them shallow node-based embedding methods, what I mean is that they are dependent on the nodes and the random walks, and there's a lot of heuristics that go with it, right? And they don't go as deep as well because we can't cover the entire graph. So instead, can we learn a graph neural network directly on the graph structure that we have by leveraging some of these compute graphs and things like that? So how a graph neural network works is each node may define its own unique computation graph. What I mean by that is each node may say, if I am connected to, I'm a node, everyone that I'm connected to 1 hop, 2 hop away, that makes my computation graph. By computation graph, it means is, imagine you are doing computation by message passing. If I send a message out of me, where all will that message go? 1 hop away, 2 hops away, etc. 3 hops away. You can keep calculating it, right? The more hops you add, it becomes a combinatorial problem then. But so essentially each node can describe its compute zone, irrespective of its degree, it's irrespective of its connection, by leveraging the message passing paradigm. So then what we can do is we can sort of create the idea of the feature transformation where I am a layer 0 where I'm just starting from, and my embeddings are my node features is exactly the same as an input layer for a neural network. I'm starting from there as a first point, and then I see how far I want to go. I will send a message, who all am I connected to? And then I'll calculate the embeddings of the previous neighbors. Do I go 1 hop, 2 hop, etc.? And then I will back stop. So if I say, okay, if you look at this equation here, I'm going to go, whether I'm going to use a ReLU function, etc., for my, or tanh as my objective criterion here, and I'm calculating the embedding of the kth layer, the way it would work is I will say, okay, if I go from first node to the second node, 0th embedding is whatever my node features may be. If there's no node features, whatever it is. Then I'll calculate my next one. I'll average it. Then if I go to the next one, my previous one is 0. If I go to my stage number 2, my hop number 2, then I'll calculate the average of 0 and 1 together. I can put those together. Right? So that's how sort of I would keep doing, I would keep building, and I would keep creating my computation graph that captures the reach of my neural network across the thing. And why the graph neural networks are powerful is that it essentially allows you to go deeper and broader into your network. Because now it's a random walk which is node-based. You start at a node across all the neighbors. It's not taking the entire neighborhood into account. It takes a path which becomes linear, right? And if I come back to that, if I start from that node again, I can maybe go to other paths, but I will miss my neighborhood invariably with a random walker. With a graph neural network, what we are saying is it's a compute graph. Calculate everything in your first neighborhood. Everybody's reachable. Then maybe the second neighborhood, second hop, between this to that. that becomes quite extensive, and then, you stop. You go, okay, 2 hops is enough. But what it gives you is a complete sense of what the neighborhood looks like for a set of nodes. Not just simply when we say the previous embedding methods that we talked about are node based, is I'm not starting from one node and taking walks and taking steps, etc. But I'm now capturing a broader neighborhood, if you will. So now we can sort of, create this graph neural network way to learn my embeddings. And now I can create my feature vectors. So graph neural networks have been amazingly powerful. They're so powerful now that folks are not using random walk-based methods as much anymore. Everyone now is, even chemistry people are just using graph neural networks because of the richness in how much they are able to capture of the neighborhood information. However, the challenge with those, the challenge that we wanted to tackle in 2019, another student of mine, Chushu, he did this work and received a lot of awards, and recently also received this paper received a Frontiers of Science Award as one of the best algorithms published in the last 5 years, was our work on heterogeneous graph neural networks. And what we did with this was that we sort of said, imagine a graph. The computation graph sounds more intuitive if all nodes are the same type. Now, what if I give you a challenge that the nodes look like this, where there's a user node, there are items that are connected. So imagine there's a user, I'm connected to a movie. The movie has images, scripts, what have you. There's genres. There's also the same author graph, author organization paper, venue, KDD, other conferences where you publish those papers, Wisdom, Web Conference, etc. Molecular reactions where I have bond strands and atoms and valence and all that information. So all these graphs have a lot of properties about them. There's text, there's images, there's attributes, there's connections, there's different kinds of connections, relationships. How do we capture this kind of heterogeneity in a graph neural network? In the embedding way that we saw earlier, we were able to solve it by doing metapath to vec-based walks, and we could create an embedding vector. With the graph neural network way, what we are saying is, can I give this kind of a heterogeneous graph to a neural network and learn from it and create a representation? Because at the end of the day, what does any machine learning algorithm need is this. If this is a feature vector, this thing in green, that's all it's looking for. That's all we are creating. So how do we do whatever learning that we do on whatever complex graphs or heterogeneous graphs or structures, etc., we want to get to that embedding layer? Because that is my beautiful feature vector. I'm going to be loving that feature vector. Because that feature vector I can use to solve, to give to any downstream learning task. And this was that paper that I was talking about earlier, heterogeneous graph neural network. So the way we sort of, went about doing this is that we started with a heterogeneous graph. And because it was we had to do certain aspects to it to collect as much neighborhood information that we could. It's still not shallow, even though we're using random walk. We said, let's do random walk with restart. Random walk with restart means is that if I'm starting at a node A, I will say, go capture your neighborhoods of, say, only of the type authors. Then come back and then capture the neighborhood computation graph. So remember, we are building a computation graph. We are figuring out how the message, if I send a message out, how far and how the message will go. So if I say that, let's start with this node A, let me now suggest you follow the path of only the author types, one type of a graph. That's a message, computation message passing framework. Come back, then follow a different one. That's a different computation message framework. Then come back and follow a different one. So I could introduce these random walk with restarts to ensure I'm capturing all the possible pathways to build my computation graph for my node. It's still doing graph neural network. We're not doing random walk based embedding, but I have to still capture my neighborhood. Because it could be that if I follow author to author based connection, it'll lead me to a different computation graph. But if I follow author to the paper, it'll lead me to a different computation graph. Okay. When I say by what I mean by computation graph is things that I send a message to as a sender, there's a recipient to it. Okay, which means that's the connectivity of things around me, one hop, two hop, etc. And then I can do type-based correlated neighbors. And now imagine that if, let's say that I go from me to an author to a paper, and if the two authors are connected because they also wrote the paper together. The two authors are connected if they also work at the same organization. That's a much stronger connection. We're able to discover that by doing so. We go, oh, wow, I was able to get to the other author by the paper. We wrote the paper together. I was able to get to the other author because we work at the same organization. And I was also able to get to the other author because we go to the same conference. Suddenly, that is a very strong computation. We need to be able to capture those connections, those strengths of connections, etc. And that's what we mean by type-based correlated neighbors, what type of neighbors we are able to get to and what their thing is. Now, and the other thing as well is that, let me just come here. I'll go show you the architecture completely. The other thing as well that we are trying to do here is, one is, remember, this is a heterogeneous graph. As a graph, we have the connections, we have the structures. So one is who all I can reach from a computation perspective, who all I can reach from a walk perspective, who all I can reach to sort of say, okay, this is my one hop, two hop neighborhood collective aggregation that I can provide to the neural network. But I also said you have images, you have text. We also need to be able to bring all that information into your feature vector too. Because at the end of the day, what does a machine learning algorithm need? A single feature vector. We can get the graph structure done. That's easy now. But hey, we also need images to also feed into that feature vector and into that 0-1 space. We also need text. So what we did is we built a sequence of these sort of layers, content aggregators, wherein we built a pre-trained features, we pre-trained on, we extracted the images, we extracted the text, we extracted the attributes, we extracted the structures, and we were able to create these individual embeddings. Imagine that these embeddings, these intermediate embeddings, one embedding is for a figure, one image, one embedding is for text, one embedding is for something else, for attributes, one embedding is for the graph structures. So we could now create all of these embeddings that we wanted to do. And then we do an attention-based graph neural network to create a final embedding layer such that we could now learn, put it all together. So what we're doing again here is, intuitively speaking, you can look at the paper for additional details because we can't go through it all. We're almost time to this lecture. And then in the next one, there's other topics I want to cover. Is intuitively think about is we have different kinds of embeddings that we have learned at the NNN1 level. One is for image, one is for attributes, one is for text, one is for graph structure. And then we're going to aggregate those embeddings. So these are all now over here in the same 0-1 space. At this stage, they all look the same because they're embeddings. Yeah? Be good? And we can do image convolutional neural networks for images. We can do Word2Vec for text. It doesn't matter what you're using, right? And they all look the same at this stage. And now we will and this is the neighborhood aggregator, which is the graph neural network. So over here, what I've done is I've extracted all the content I needed. Over here, I've done the neighborhood aggregator. And now I will mix them all together with an attention-based network and optimize the loss on this and create the final embedding there. Are we good? So now it's essentially a very clever engineered solution where we are able to leverage everything else that has existed. We have been learning neural networks with deep learning on images. We'll be doing text. Easy. It's how we now use them together. And we describe the attention type as well, because you need to be able to tell that what you want it to be, for a loss function, etc. All right. So I think this is actually a good, I know we had until 10:15 or something, but what I'd like in the second session, we'll move on to this, where the second thing that we want to, I'll give you an intuition now, and then we'll come back and go a bit deeper, is oftentimes a challenge that we are seeing with the graph learning and the graph neural networks and all of that space is that we can learn these embeddings layer, we can learn the structures, we can learn the encodings, we can do everything, but as we are moving more to the supervised learning space, we are having the tail effects problem. So that a lot of graphs, imagine that somebody comes and tells you that label every single thing of Facebook or Instagram or Snapchat or anything else which is not labeled today. It's an arduous task. Or even chemical reactions. To appropriately label a chemical reaction, to say, for these properties, you have to done a wet lab test. You can't just do computer-based. A chemist has to take what you have suggested about a reaction, test it in the wet lab, and come back to you by saying, hey, I did the test on the wet lab, this property holds. It's very expensive. So annotation is a problem. So how do we, when we are collecting high quality graphs with limited label data, how do we sort of do learning? What we have spent time until now, until this stage, is how do we extract X in an unsupervised way? Now, what if I tell you that this problem has some supervision signals to it, has some labels available? How do you capitalize on that and improve your learning to get to a better feature representation? All right. So, and we know everything cannot be labeled, it's too expensive. So the challenge is, it's not just learning X, because we can do that using graph neural networks, etc. But it's also using a bit of the Y, your labels, but you don't have all the Y. But you have some Y, some labels, and I want you to use them. But how do you use them such that you have a much better representation that you have learned, a much better X that you have learned? So in the downstream task, you're now doing much better than you would have with only doing X. You cannot get all Y. Are we good? So we'll come back to this when I see you in the afternoon. I can see you all looking a bit tired.
Sorry.
I should be more tired right now, though.
It's fine. So they have a small break now. So next lecture about RAG and LLMs, and then your lecture is and then we have coffee break up here, and then we have your lecture. And maybe we have some questions, because we have actually few about 10 minutes of time for questions. And may I ask if I had master diploma this year, and I proposed the idea of research like this. It was quite a bit of funny. I take an image of maze and put it in the LLM and ask to answer, is it the out of this maze? Can you find an out? And we try to do images, graph representation, and matrix representation in a text form. And text representation obviously was the best one. Not too good actually, because basically we want to we ask to apply algorithm without explicitly mentioning algorithm. So but it was like about 40% accuracy for mazes, like 6 by 6. So my question is it possible to change representation and edit and maybe give understanding from different angles of the problem.
That's good. And I don't know how. So if there's a maze, if you could sort of capture you could give addition, you can do if you're using LLMs, right? You could provide a knowledge graph as to what are the other kinds of mazes that exist, how people have gotten out of there. You can do RAG, retrieval augmented stuff to optimize your prompt engineering. That's one way. And the other way is, what if you can actually represent your maze as a graph? Right? So now you know from this point to the other point, what if they are random walkers, what will these random walkers do on the maze? Right? Can you represent it as a graph and then see what happens? Then do you even need an LLM as a result? I don't know. It's a really interesting problem.
Idea actually was to test an LLM. I mean, to check is it good or bad in these capabilities.
What was your result?
Well, result actually was not very good because actually students failed in master diploma defense. Well, not because of the problem, but because of his work actually. But yeah, but they yeah. That's unfortunately. Any other
So GNNs and heterogeneous GNNs are quite computational heavy because we need to train model parameters, we need to create computational graphs for all nodes in the graph. And my question is how to speed up that? Is there any ways, maybe batches or so?
So the question was, these graph, and they are expensive, especially if they get larger, right? And one way is, of course, you restrict the neighborhood. You only go to one hop, don't go to two hop, etc. And the other is something that we have done is pay the cost in training because they are expensive for training and inference both, right? So what we have done is once we have done that during inference time, we have trained a multi-layer perceptron, which is linear in time, right? So you take a graph neural network to extract the quick basic structures that it can, because there are no other perceptron and others want to do it, and then take that first layer of information, give it to a multi-layer perceptron, learn a multi-layer perceptron, and then use that for inference time. That sort of really speeds up things. So we have a couple of papers on that in the past 1 year as well.
Okay.
But it's not solving the graph neural network computation time. And the way you typically solve it is by you could parallelize some of the discoveries because every node and its neighborhood is independent of the other. Right? So if you have multiple nodes available, multiple compute nodes available, you can just distribute them because they are independent tasks.
Okay, thanks.
Any other questions? Yes. The way you do is you sort of, what I would suggest, read up is the one hot encoding approach. Take one node, you make this one, then plus the zero, and then you do it for every node. Every walk that you're doing becomes, and then you
Yeah, thank you for your lecture, Nishish. And my question is there some interesting applications of graph neural networks and graph ML in general in computer vision?
Yes, I believe so. I think so. Basically, scene explanation. Imagine that you're given an image. It's a scene. Can you segment the scene?
nowadays?
How they've been applied, but I've seen papers which have done this,
Okay.
but I don't know if it's something that's gone in a computer vision or a video application. Robotics, I know it has gone into, but I don't know if it's general vision understanding, or vision explanation, if it's happening like percentage.
Yeah, clear. Thank you.
But talking about modeling how spreading the risk between the banks, how you can with the practical view, you can deal with this using the random votes in the graph.
Could you explain that? So you're saying that the way in financial transactions could be is, are there transactions that are connected? Let's say if I send you money, you send money.
Yeah,
you
and when we send some money, transact some money, we also share the risk in the financial institute because we share the amount of liquidity and the amount of some.
Yeah. So the question is that as you send money between entities, you send money from A to B, B goes, they send the money to C, D, you can create a net, right? But then you can have content about that node. Remember we were talking about the nodes where images, content, where you could actually have liquidity information, disk information, and all of that. So you could now capture that information into your heterogeneous graph, where you have content associated. Now you can learn risk model that says, okay, these financial institutions, these properties are sharing money from financial transactions. Or if kind of transactions are, this is indicative of money flow. Those are the things that we have done.
Thank you. Thank you.
So hello and welcome back. Yesterday we had a session about the LLMs, and today we will continue from where we finished yesterday. And afterwards, after we will finish with the theory, we'll continue to the code. So I will show you some kind of how to build RAGs and how to train a model and so on. So basically today will be more practical example. And also Alexei have added me to the Google chat, so I will share all the materials afterwards with you. All right, so quick recap of what we've been talking about yesterday. It was actually the LLMs themselves. So what is it, how it works, and so on. And what we have finished on is the problems that you got when you try to add your LLM to the production. So basically, we started with the cost of inference, and we finished up with that the cost is quite a thing to be aware of. Because even if you are using the ChatGPT or some other hosted model, the cost is still quite big. At the same time, I think that some of you may don't know it. You have an ability to actually use the models hosted on the Hugging Face, and it doesn't require you to have this kind of compute from yourself. So actually here you can see the in some models, so they don't give you the API for the biggest ones, but actually if you take a look at this inference API, so they provide you with a way to call the model, and basically with this you can reduce the number of different compute that you may want to have to run the models. So that's if you are considering the cost of inference. The other thing that you need to consider is the latency. So as you know, in the modern world, people don't like to wait. People like to take a look at the TikToks and so on, and so they don't like to wait and when something is not working, they try to refresh it, to try again, and so on. So basically, if you're doing something that is a little bit, I would say, less costly, like for example, using the Hugging Face API, it may give you the big latency. So actually, it may not be suitable for the production use. Then here comes the thing that is called the LLM scaling laws. And these laws is like the number of parameters, and we have defined what the parameter is yesterday, right? So this is a kind of experimental law. It's not the theorem that was like доведена, okay? So it's not like a theory, it's like more experimental law, but as you can see from the picture, there's always some kind of sweet spot with the data versus parameters. So basically, the bigger data set you have, the more parameters you can actually use in a way that they will actually work. So as you can see here, that we have this kind of linear scale, I would say. But at the same time, I think that wherever you are trying to take a look at your model, you have to check what is going on right now, because as we also talked yesterday, the model number of parameters per model is instantly growing, and it's growing. So basically, this is not the kind of flow you have to follow for all your life, but it's more like a like a Moore law, where it says that the number of semiconductors is doubling every now and then for a couple of years, I believe. So Apart from latency and apart from cost of inference, there's also interesting ways to deal with the problems that you can have with your model in the production. And one of this is prompt tuning, and when you are actually tuning not the prompt itself, not the text that you have, but actually you're tuning the embeddings. This, as you can see, so this is this was quite a good technique back then when there were like T5 model, and I haven't heard about it like past GPT-3, but I think that it's also the way that you can take a look if you run out of ideas how to tune your prompts. This one we have already spoken about yesterday about the fine tuning. Yeah. And yeah, if you are using the LLM in some kind of production environment, and we have talked with you about the chain of thoughts, then actually you can create the flows of the tasks that you have within your LLM. And here you can see that you can have like the sequential tasks, the kind of tree of thoughts work. You can have some kind of algorithmics way of flows that LLMs can do. Yeah, and the most important thing I would say that is most people use when they using LLMs is actually using the RAGs. So what's RAG actually? RAG is retrieval augmented generation, and it gives you ability to use your data with the model without training the model on your data actually. We will talk in details and take a look how it works actually. But here is the actual thing. So basically you can have the RAG itself. I think I had some kind of, yeah. So here is the vanilla RAG, as we can say. So you've got your query, right? No, let's start a little bit further behind. Let's try to a little bit draw here. So basically you have your documents, right? Something like that. Documents. What you're doing is actually putting them into the model. So here's, you got your model. And afterwards, you got the embeddings of your documents. So basically with this, you're actually getting the vector database that consists from the embeddings, like from your documents. And what happens next? Next, you got this query. So you are asking, for example, you have the documents that that had the transcript of all lectures during the school, right? And you want to get understanding like what was said about the LLM scaling laws. And you are like querying the LLM and actually like asking itself, asking the model within the word. Like you are typing the words like, tell me about the scaling laws of LLMs. As we have all transcripts gone through the embedding model and we have the embeddings put into the vector database, we've got this retrieve step. During this retrieve step, what happened is actually our query goes to the same model. We've got the embeddings of our query. And then it happens what embeddings is passed for. So we are getting the similar embeddings. We are getting the top, I know, 1, 2, 3. It depends on how you designed your system. But you're getting the embeddings out from your vector storage and then put it inside of the LLM with as a context. So for example, here we've got the chunks of the text that I was speaking about the scaling laws, right? And the question about the scaling laws. So the prompt will look like something like context, blah, 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 question. And here comes our question that we were typing in text. After this, we are putting it into language model. And after it, what we've got the model that got the additional context, the question, and we are actually generating the answer based on this. So we are not relying on the knowledge that model got during the training. Instead, we are relying on the knowledge that we got to the model during this retrieval process. So this is like the vanilla RAG. That is, I would say, the most common way of using it. Yeah, sure. Yeah, that's a good question. Thank you. So actually, when you are putting your documents into this vector database, the point is that you are divided into chunks. So as you remember, the model has the parts that is like the context window. So basically, it's the number of tokens the model can take in at one time. And you're dividing these documents into the chunks that make sense, actually. So currently, models have quite a big context window. So you don't have to divide it by, I don't know, sentences or paragraphs. Rather, you can divide it like by some kind of topics or something like that. And that will be actually enough. But you're right, if you are not getting the correct document out of the vector database, you will not have the correct answer. That's actually the problem. And if you don't have the whole document, you will also like your answer will be based on this small part that you got. That's why we are taking out of the vector database not one document, but usually it is some kind of K documents where you can decide the number of K. It may be like hard-coded statical, or it may be some kind of threshold of the things that you take a look, is it relevant or not? And you got some score about it. Actually, here we comes to the second way of getting the data. So we're like now talking not about the vanilla RAG, because all these questions that you addressed, they are actually like problems for the vanilla RAG, and that's why people are coming with more and more complex systems. But this systems like has more of the engineering complexity, not like the scientific one. And so, for example, we've got the iterative retrieval, right? So here, like imagine the same things that we were drawing, and here is like the same thing, but we have a couple of iterations of what is going on. And in this case, we can get, for example, several different answers from the LLMs, like with taking one document, 2 documents, 5 documents, blah, blah, blah. And in the end, what we've got the several different answers, and we can compare them together, like one against another, and give the user the most, like, the one that we choose is like better. Also here maybe like the whole lot different of other schemas. So for example, like we have the post hoc retrieval, so we are checking if our answer is actually relevant. So we can add it here as well, so we can check how our answer is relevant. We can add another LLM as a judge. So for example, you are using for example, Mistral for generating the answer, and then using GPT 4.0 for judging it, and so on. So basically, I think that the ways you can combine all these pieces together is limited only by your imagination, actually, and the way that you want your things to get from it. All right. So actually, regarding graph, it's not only with these documents. There's also some different tries of improving it regarding all these problems that we started to talk about. And as you can see, like there's some kind of multimodal retriever graphs where you can put the image inside of it, get the embeddings, and then get the text output. The same goes with videos and so on. So this is regarding the multimodal models. Then there's like ensemble of RAGs where you got the several RAGs stacked on one another. So if you are familiar with Kaggle and you were doing some Kaggle competitions, you're familiar with stacking because it's quite popular there to get the better and better results. But it's quite heavy, as you can imagine, because you will have like not one request to the LLM, but rather you will have more and more requests, the more complex system you will have. And so we're returning back to the cost of serving all this stuff. And it will increase, obviously. So this is LeCun limitations on autoregressive models. We've been talking about it yesterday. And here we comes to the thing that is called hallucinations. Yeah. So as we were speaking yesterday, you probably remember that that large language models are very often hallucinate. So they are generating text token by token using the prior knowledge they were trained on, and so on. So basically, when they are, instead of saying, I don't know, they are trying to give you the answer, and they are producing some kind of text. It's called a hallucination. There's like different ways of hallucination. I think you know that LLMs are usually quite bad with numbers. So here's like the things that they are missing some numbers or changing them and so on. Like it's a factual hallucination. So for example, it's missing not only the number, but the person as well, right? And here's a faithful hallucination is when it's missing on a number. And actually, as you can see, so there's a question and the answer based only on the prior knowledge, only on the knowledge that was put into the LLM when it was trained. So actually, like if you were using RAG for this, you will not get these hallucinations. Yeah, here will be a link to the hallucination survey. There's an article with like 50 or 60 pages long, and it contains the taxonomy of hallucinations. I would not say that it is that you need to read it, but you can go through it like in diagonal and take a look, because it gives you the understanding of how you can classify your hallucination, give them a type to understand what actually they were doing. Yeah. So here, as you can see, the like a lot of different ways of dealing with hallucinations. So actually, you can use some kind of metrics to control it, because like everything that we are doing in data science, we can measure up and we can like use some kind of metric to determine whether it is a good result or a bad result. So here's a fact-based metric. It's I think it's one of the most common. So actually, you are extracting facts and comparing that facts. Again, you can do it in different multiple ways. So you can, for example, extract the entities out of the text and compare the entities one by one, or you can make embeddings out of your facts and take a look wherever they are same or not. Here's the other way is to use another model. So NLI model is a natural language inference, I guess, entitlement. So basically it is when you got two different texts and the model should say wherever they are, do not contradict to each other. Basically, yeah, let's take a look. So this is the famous SNLI, Stanford Natural Language Inference dataset. And so basically the model is a classifier that trained on something like this. So you have the premise, the one sentence, and you have the hypothesis, the other sentence. And then you have the labels that are neutral, contradiction, or entitlement. Basically, this one is a classical data set. It's not recommended for usage anymore because it is very like it is very simple to get good score on this. So actually, I think you can do it with some kind of TF-IDF and logreg even. But if you are doing an NLI problem, this may got very complicated. Imagine that you have not only the one sentence here, instead of it, you have like the articles, like news articles, right? And you need to understand wherever they contradict one to another. So I had a student who wrote a diploma on making the systems that would to understand wherever these news articles are about the same topic, and then are they contradict each other or not. So we were doing it for Ukrainian and for Russian because we wanted to make it as a disinformation detection engine. And actually we did not come up with a whole system. So because it was for Ukrainian, it was quite hard to make an NLI model itself. So we are still actually in process of improving this. But actually what we came up for is using the RAG and the graphs, the RAG graph. I will not go into detail with the RAG graph because you have enough of the graph lectures from the other lectures. But the idea is that there's no like the NLI data set that you can use, for example, for Ukrainian. So this is the field where you can also make an improvement and then make a paper for example, UNLP conference. That would be very also appreciative. Yeah. So regarding the context lengths and construction, so basically each model has the context lengths, as I already said. So basically, if you are putting more and more context, the model could not use that context because you're putting too much context. At the same time, when you are dividing the information by chunks, the model would need to understand where the one chunk finished and wherever the second chunk is the continue of the first chunk. So you have things that is called the overlap between these chunks. Basically, you have the one chunk, and if you take a look at some kind of popular libraries, like LangChain, for example, they have the overlap parameter between these chunks, and it is usually set to from 10 to 20%, actually. Yes, different modalities. I think that we will not go through it, but there is a logic llama also, like this is related to the graphs. So there was the NFL logic, first order logic actually, way of trying to understand, but doesn't work properly. So very cool idea. And if someone wants to play along with it, you can go ahead, but it's not working. Then, yeah, sorry, we are a little bit jumping from topic to topic, but we were talking previously about the serving models. And here's the one technique that can help you also to serve models within having like not that much of compute power. So this method is called quantization. And actually, like if you know, the parameters are stored in 32 bits. And if you are reducing the mantissa part of the parameters, you got a smaller amount of memory used for your model. And that's why you can serve the larger model on not that big, actually not that big server. So yeah. So the point is that you're reducing the number of stored parameters, and you're not like when the computer is when you're making an inference, you are using the full mantissa, but when it is stored, you are storing only half of it, for example. Yeah. Yes. Yeah. Yeah. You have a little reduce of accuracy actually for that because you're not storing the whole data, whole information, but it's like up to 1 or 2%. It's not very relevant. So you're not losing a lot of accuracy. And the last thing what I wanted to present to you is called LoRa, and LoRa is the way that people came up with a fine tuning of this large language models. So as you can see, you have the pre-trained weights, right? And these pre-trained weights, they are very big. They have been trained on lots of data, and to retrain them on your data is taking a lot of time, right? And time, efforts, data, and so on. And if you will be training it on your data, they will be actually losing the prior knowledge. So it's like the vanishing gradient problem, the same, like not the same, but you can make an analogy between them here. And they will be forgetting the data that they were will be forgetting the data they were trained on. So what people came up with, they got this pre-trained weights, and we are composing the low rank matrices, and we are training only them. So actually, we are training on the first and the last layer, and then we are concatenating it with the pre-trained weights. In this way, we can save all the data that was that the model knew before, and add a new information that we've trained on our data. And as we are training it on our data, so as we are training only a couple of layers, then we are not like, we don't need a lot of power and a lot of compute to do that. In this way, we can like actually use it to make training on having not that much data in our training data set. Remember, I told you yesterday about the Hutsul training project, Hutsul dialect training project, which I was working on. And so actually this one is a method that we have used for training our model on our translation data set from Ukrainian to the dialect. Yeah. Yeah, thank you. We are continuing to the next lecture that I was intended to start for today. But no, first let's go and take a look on the training. So here is the Kaggle. I think that most of you know this. I will share this notebook with you as well. The only thing that to have the accelerator on Kaggle and the internet turned on, you have to verify your phone number. So basically, yeah, before it, you should do it. Here is the GPT-2 because it's much smaller model than GPT-3 and so on. So we are just taking it as an example. You can use the same techniques over the more complex and bigger models as well. So here is a diagram of GPT. It's okay. So we are importing the torch. We are importing the model tokenizers and so on. And we are importing the article from Kaggle as well. So you can take other data set from Kaggle. That's is not important, but this one is also available on Kaggle, so you can use it as well. So as you can see, the data set is quite small. We will need mostly the content out of it. The other meta information is not very relevant for us at the moment. So we are initializing the GPT-2 tokenizer and model. And when you say from pre-trained and say only this small, I would say like pass, not the whole pass, it will actually go to the Hugging Face and take a look there. So basically, if you will go to the Hugging Face and search it here, yeah, here it is. So as you can see, we've got the same URL here, and we have the way it can be used here as well. Yeah, and when we say from pre-trained, it gets you all this data straight from the Hugging Face, and you are like getting the model. That's why you need actually the internet turned on, because otherwise it will not get you the model from there. Yeah, so we are taking the content out of our data set, setting our maximum lengths. So actually, this is the context window of our model. And then we setting the padding. So actually, if we will be putting the input to our model smaller than the maximum context length, we will fill it up with empty tokens. So actually, all the inputs will be the same length. Then it is what we are doing. We are converting our input to the tensors. We are creating the function to do it, and afterwards we are creating the data set. Here we set up the device. So actually that's why we need the GPU. Otherwise it will be very slow, even for GPT-2. Then we are making the model optimizer, and we take a look at the batch of our inputs. So actually we are taking the example from our data set, convert it into the tensors, and then make batch of those tensors. The training loop is very simple here. So I have put only one epoch here. It's obviously not enough for real world training. When you are training some models like Mistral or something like that, it is it's usually like from 3 to 5 epochs that you need to train. If you're training more, then you will be overfitting in most cases. But here we just do it as for an example, so it's okay as well. So as you can see here, we are just actually taking our batch to device, then taking our output, calculating the loss, and making a step. That's really just standard way of training the PyTorch models. We are saving our model like in the working directory, and then we can use it here from pre-trained, and afterwards we can use it for the inference. So as you can see, we have not created a very great model here, and it has generated some kind of text that is literally looks like a text, but at the same time, it makes no sense. It replicates itself. This is a part of what we've been talking yesterday, because this model is using the greedy algorithm for getting the next token. So this is the way how you can train the model. This short tutorial, I will share it with you as well. And afterwards, let's take a look of how we can build a RAG, because this is I would say more interesting to you from the practical standpoint. So again, this is a simple RAG. So I can call it vanilla RAG, and you can improve it and add more and more layers of complexity here. So as you can see, no, the models are used with RAG. So RAG is not the part of the model. It is the, I would say, engineering system to get the model work with your data. No, so for let's get back a little bit. So actually, when you have your ChatGPT, right, and you are here, and you say like, hi, how to cut the stop sign, right? So this is what we need to know. So as you can see, it gives us the understanding that it uses its pre-trained weights. So there's no RAG involved here. It says like, okay, probably you want to cut it out of the image. Good. But what we can do, we can get some kind of document. I'm not actually sure. What document can I use from here? Okay, let's. Give me a second, sorry. All right, so for example, here is some kind of Python file. Let's take a look at it. Yeah, so here is the class of the preprocessed data, and it's doing something. Don't remember about it anything, but what we will do now, we will create a new chart with the ChatGPT, right? And we will put this file. We'll put this file inside here. And we will say, describe what, for example, drop outliers function is doing, right? And here you see that it actually like is analyzing. It says because it's reading this file and it's answering based on the question that I like on the context that I provided to it. So in this example, it's a little bit artificial example because it's taking the file, searching through file, and probably the ChatGPT has the context to put the whole file there. It doesn't need to break it into chunks and so on. But imagine that it has a smaller context window, so it doesn't fit the file. So in that case, under the hood of the system, not the model itself, it will have the vector database where it will put the chunks of the file. And then when I was asking about the drop outliers function, it will go through the chunks, find the drop outliers function here in the chunks, take it out, and then based on that, it will answer me. So did I answer the question? Yeah. Kind of. Yeah, kind of. So as I said, you can increase the complexity by adding more layers of search, more checks of this answers and so on. Yeah. Yeah, and if we will, for example, ask the same thing starting from a new chat, right? It doesn't know anything about the function, right? So it will just create the random things that it may be helpful for this question. All right, so let's get back and take a look how we can build the RAG themselves. So here is the grocery data set. It's, as you can see, it's the data set also available in Kaggle. You can see some kind of different desserts, products, blah, 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 with their title, features, descriptions, and so on. So we will be using it as our files. So as we just used the preprocessing file, we will be using this whole data set. And as you can see, what we are using here, we are using the LangChain. The LangChain is a library that is mostly used for building these RAGs. We are using Faiz as a vector database. So I think it's one of the most popular databases. So for example, the other popular choice is a Helma database, but I don't know, here I have used Faiz, it doesn't matter actually. And we are using our Mistral model. It's not a big model with 7 billion of parameters, and it's already present on the Kaggle, so we don't need to actually load it, right? Here is the pipeline. I think that's the one that we have already seen, and I have added the drawings of it. So here is our documents, in our case, our data set that we have here. And we are passing it through the embedding models, putting it into the vector store. And then when we have this query come from user, we are asking our embeddings from the vector store to get the right context. That's what we're doing. And getting the right context out of here, we are passing it to our LLM. In our case, it is a Mistral LLM, and we get the output. Let's take a look how it is done. So first of all, we read our data set. Here is nothing, bless you. Here is nothing like strange. We are just reading the CSV, dropping an A, and so on. And then we make a function to get the product description. So we, as you remember, that we are passing the text to our model. And so we're building some kind of text that will consist from product title, product category, product features, and description. And as you can see, we are adding it as a column, which will name the full description, and here it is. So the product title, and we are taking the title from here, the features and description. So this is example, product title, right? David's cookies, peanut butter cake, blah, blah, blah. Product category, bacon and desserts. So this is the whole information actually that we can get from our data set to present into our model. After it, we are making this step. So we are taking the model, and in our case, it is this model. So it is all many model. It's the embedding model. So as you can see, it is in sentence transformers. So this is a sentence transformer model. It maps sentence and paragraphs to a 384-dimensional dense vector, and can be used for tasks like calculating semantic search. So semantic search is what we want from it. So basically, you can search through this sentence transformers models that is available here, and these embedding models. OpenAI provides its embedding models. Any, I don't know, cloud provider also provides its own models for it. But yeah, you can also, this is a way that you can use different models to get the embeddings, and it may increase the accuracy of your search as well. So you can try different models here as well. So here what we do, we are downloading this model, we are putting it on the CUDA device, and we are adding our, actually like our data. So we say that here is like, in LangChain, we have this data frame loader, we have PDF loaders, and so on. So basically, if you can go to LangChain itself, here you will have this integrations. Yeah, and here you have the text loader, the document loader. So you basically can load not only from the data frame, but from all other documents like PDFs, text documents, and so on. So what we are doing, we are creating these documents, and we are adding them to our place vector database. So as you can see here is the commented code. It is commented because we don't have the large descriptions. So the Mistral has enough context space to fit in all the descriptions that we need here, but actually here you have the chunk size, the overlap is what I've been talking about a little bit earlier. So you have the chunk size, and wherever these chunks are going one by one, you have this a little bit of overlap for model to understand that these chunks are connected together. Yeah, but we don't need it now because we have the actually everything fitted in. So as you can see, now we can query our FAIs from the documents with using the text. So if we say like cookies with high peanut butter cake, and we are getting the document out of it. So this the document gives us the subcategory, price, discount, and so on. So actually everything we need to know. And in this case, what we achieved, we have created a storage where we put all our data set, and we now query it using the text. Yeah, and here's the K parameter that says like we need only one answer out of it, and we can like change it to 5, 10, and so on. And so you will have the more and more actual documents retrieved from the database based on the score of similarity. And then it seems good enough already, but then if you want to get the answer on your questions, then you have to go the same way with your query. So actually what you are doing is you are using the Mistral model, the LLM that we are using, and we are loading it into the memory here, into the CUDA, and we said that the task is text generation. Maximum tokens is what we expect the model to generate, because if we will set more, it probably will generate some kind of hallucinations as well. So basically, what we are doing, we are creating this long chain pipeline that we will be using our phase graph. So here you can see the prompt template. So actually, this is the instruction that what we are telling our LLM, what it needs to do. Then we put the context, the things that we retrieved from our database, we are putting in here. And then we are getting our question, like the same one that user has been asking. And so we are putting the context and question in our template, creating the LLM chain, and using our FAIS as retriever. So basically, we are retrieving these documents out of the database. Yeah, and in this case, we got this. So for example, we say, like, tell me about David's cookies always. And it gives us the description, and it's not just giving us the description itself, but it making it look like the description of something. So actually it's telling you about the product. It's not just giving you the text of the description, as you can see, because what you got the description put into Mistral, and you got the question put into Mistral, and then it gives you the answer. The same thing, like if you're asking what is the price, it will gives you the price is $56.99. Why it is not generating more tokens? Because because we have set 200 tokens of generation, but it generates the end of text token, and that's all. Because the models understand that they need to actually stop generating after this token. And so on. Basically, even if you say something more complicated, like list top products under beverages category, and it will give you these like names, right? Actually, you can see that you add show only names here, and it is important because when you are using models, they don't know in what way do you expect the answer to have. And adding these short instructions inside of your query is quite important to get the most relevant information that you can get from it. Also, I need to mention that these open source models, like, these are getting better actually over the time, but sometimes you can see that here they would say like, if you don't know, just answer, I don't know. And in most cases, if you are using some proprietary models like OpenAI models or Cloudy models, for example, they will answer you, I don't know. But most of open source models will hallucinate and try to make the answer for you. So cool. Okay, so basically they should understand inside of the model wherever the context is relevant to the question. But that's the point, that the open source model are not doing that. in most cases. So they are trying to hallucinate despite of the context. The way is going back to the RAG itself. So inside of the model, you're not doing it, but you're actually getting back to the RAG, and you are checking wherever the context is similar to your question. Like you are, I don't know, the most, I think that the most relevant thing is to get the NER inside of it, get the entities, and check wherever all the entities needed is present in the answer. So if not, then you are saying, it's not very good. And you may get the integral score out of it and say that, for example, if the context is not passing your threshold, then you are not showing anything. And you just skip the LLM step, just answering, I don't know, directly. So yeah, but this threshold that it must be defined in all the cases, you have to get it empirically. I mean, so it's not like the numbers that you can get out somewhere and just put in. Yeah. But we are not training here. Yeah, but it was a fine tuning of the model. Here we are talking about RAG. For fine tuning, you are actually got the labeled data set, and you are as usual training. Yes. Yeah. Yeah.
Of to estimate quality, how the large language model reproduces numerical information or some numbers or dates in RAG response.
So in RAG response, if you want to get the same number that you retrieved from your database, you can just compare it, like if it's the same number or not.
Yes, I see, but could we do it automatically? For example, suppose that I am developing a RAG system, and I need a pipeline to improve it. So I need to measure quality of it and get a number of this quality.
I think I will answer it a little bit later, okay? Because we will talk about one kind of metrics that you can use for nearly the same things that you're talking about.
Okay.
Yeah, imagine we want to have like a conversation on our data. So we have RAG, and we want to have a chat about this like data. And LM was not trained on our data. We're using RAG, which is interesting. How can we also enable this conversation capability so the model can understand our its previous answers, our previous questions about that data, and which in our RAG. So just interesting how we can make such conversations.
So the same way that you have the conversation with the ChatGPT. So actually you append the new, you got all the context, all the previous conversation, and you append the new question beneath it. So you are, every time you are asking the model, you are passing more and more data in it. And if you're getting to the context window size, you make a new request for the model with like summarize the first half or something like that, and you just reduce the number of contexts. So it will not be remembering all the details, but it should have the main points from it.
Okay, so.
All right. So moving next. So yeah, here is the RAG. I think I have showed you how to do it. Now, I think someone yesterday also mentioned that there is an agent, and the agent is a way to deal with the LLMs. So here is the hallucinations types. We already talked about it. This is a cool example. Let me take a look at it as well. Like the same prompt, but with different word. Yeah. This is the rag. We already seen this, and here we comes to the agent. So here is things that is called React, and it's not the front-end framework. This is reasoning plus acting, and name React makes it a little less Googleable. So, but at the same time, you can go to their initial paper, take a look at it, and this one is really worth of reading. So what is React? Reasoning and acting, right? So what is reasoning is something like chain of thoughts. What is action? Action is something that can do things in a real world. So for example, what agents can do. When you are using the LLMs with RAG, you are not dealing with any new data. But when you are dealing with agents, you are adding actually the possibility to communicate with external systems. So basically, if you want, for example, to say like, hey, model, please book me a ticket from Kiev to Lviv on the 7th of September. And usually the model will not do it for yourself. But if it can communicate with external systems, it would probably get you the correct context. It will create the correct request for the system and may book you the ticket that you want. So this is what React is. This agent is something that you can see in ChatGPT, for example. There's a lot of different plugins there. There is a ways that you can use all this stuff and for different things, right? I think one of the most famous is a Wolfram. So actually, you can ask some kind of mathematical questions for the ChatGPT. It will generate the Mathematica code, send it to Wolfram. It will execute it, and it will actually get you the answer, process through the LLM, and show it in the way that you would like it. This is also the React example, and there is a lot of different agents. So as you can see, like starting from Wolfram agent on ChatGPT, then we can go to different other specialized data agents. So the good example here, and we will be talking about these data agents. And the good example here is some kind of agent that helps you with your email, right? So you've got the email, then it builds a reg out of it, so creating a knowledge base. Then this other agent is creating the answer for you or some kind of update for you, and creating some kind of update here. So it may be like update going on Slack. For example, if you are getting some kind of emails that you need to respond, but you are not reading emails, you are a cool guy or girl in a startup, and reading emails is not very cool, and you need your Slack updates for it. So this agent can help you with that. The other way is if you have the emails coming and you need the draft of the response drafted quickly, so you don't want to sit and write the response for 30 minutes, and the data agent, knowing the previous chain of your conversation with these people, it will generate you the draft. You can a little bit change it and send it. So basically, how these things works. It works with some kind of conversation history is basically what you've been asking. So we are using this conversation history as a context, actually. That's why I think you notice that ChatGPT is saving all this stuff on the left and give you ability to continue with that. So we have the conversation history saved here, and we have the tools. So in these tools, I mean that you can use different tools. You can use this Slack. You can use this request for other system, for example, for the booking of the tickets and so on. And this loop is a reasoning loop. So actually, we are not restricted to only one action. Your agent can go to one tool, get the answer of it, go to another tool, get the answer out of there, combine it together, and give you as an final answer. So actually, this is a kind of process that is going on with the agents. So this is how we can use the agents, and basically here is how to, if you would say like how to handle the big responses from the tool. So for example, you are querying for additional context in Wikipedia, and it gets you like the great amount of articles out of there. And so you can either summarize it or build a reg out of these articles and then get the things that you're interested on. And also here there's things that when you have the large number of tools in this loop, actually, the point is that your agent can be confused. So it may go to the wrong tool and get the wrong answer for you. So there's also a possibility, and that's why it is recommended not to use more than like from 3 to 5 tools. Like the 5 is the upper limit for one agent to actually like for one task. So because what I mean that for different tasks, you obviously can have different tools. And you were asking about how we can measure the confidence. Here is the metrics that is used inside of getting the answer from these tools. And I think this is a great metrics that they can be used very widely, and I would say that they are quite standard now. So here is the groundness. It evaluates how well the model generated answer is aligned from the input source, right? The relevance. So it measures the extent to which the model generated response are related to the given questions. The similarity, and yeah, it gives you the some kind of number that is for this metrics, and you can use it actually. I think you have a question. Yes. Yeah. I'm not sure, but that may be a case, maybe. In that case, I think that you would need to write down the kind of how to calculate the metric yourself. Probably yes. I saw some papers, but I have not read them about this. So there were no such cases in my practice when I needed it directly. So like I put it somewhere on the other tab that where I would never read it. But yeah, probably there is some kind of already some kind of advantage in this area as well. Also, as you can imagine, when we have these agents, they are making requests to these external systems by some kind of APIs. And if the internet fails, for example, or we don't have any access to it, to the tool, or tool fails, or whatever, then our model will most probably hallucinate. So that would be up to you to prevent it and to make this restrictions for the model to either to say, I don't know, or to detect that the tool were not used and you don't, you have no like way to get the right dates, the right answer. So here is the regs, right? And if we are adding agent, we are getting the same thing as a reg, but you are adding a little bit another step in it. So you're adding an agent here, and this context, you are checking this context relevance. And yeah, here is a good best practice for agents, and I will show you now how, yeah, we are practically out of time, but I will show you how it works anyway. So basically, I will share this notebook with you as well. So as you can see, we now using this Llama index library and TrueLens eval library. So there's a lot of different tools for comparing agents, comparing relevance, and so on. And even if you will take a look at my, I think, most advanced tool, that's the tools that I tell everyone to use, the MLflow. It has also very, it has already the LLM part in it, but it mostly focuses on using the OpenAI models as a judge model here. So we'll take a look at how it can be done with TrueLens today. So we are like installing libraries, nothing interesting here. So here we are setting up the OpenAI key, then the Yelp key. Yeah, this is my key, so I will delete it before sharing it with you. So what we will be asking is actually we will be asking about something somewhere. I think you know what Yelp is a platform where you can set the reviews to some restaurants and so on. So basically, we will have this Yelp as an external system for our agents. And so what we have the OpenAI agent that is answering directly from OpenAI. And we have as well this OpenAI agent that will use Yelp as an external tool to get understanding. Yeah. So here we have a lot. Here we have our standalone application with GTP 3.5. Yeah, I think that it's like I have this example for a couple of months, and probably will need to change the model already. And here we have, oh, let's run it all, because otherwise I will not be able to show it. So here we got this TrueLens that we are starting, and actually the custom OpenAI agent that we adding the prompt with is actually asking them to provide our metric and to decide wherever it is a good or where it is a bad one. And so what we are doing here, we are creating the custom OpenAI agent, and we are starting to make our queries. So the queries is like something about San Francisco restaurants, Toronto restaurants, and so on. And after it, we can add the Yelp agent. So it is the same agent. It will be using the same model, right? And just it will go to the Yelp, ask the same thing out of it. So, for example, we are asking about the best pizza in New York, so it will go to Yelp, get the pizza places with the most ratings out of it.
Yeah, I have a small question about the agent and Yelp communication. How does the agent knows the Yelp interface, or it's pre-built so and you take it like out of the box as a dedicated Yelp agent, for example, dedicated Facebook agent, Twitter agent?
Yeah, so good question, thank you. So we have the Yelp key here as well. And yes, they have the pre-built agent for this case. So yeah, and if you want to build your own agent, you will have just to create the API request for it and so on. But for big things like they created these agents to have the integration. And afterwards, what we have the same questions and the answers from the Yelp as well. And if we take a look here, we started the dashboard somewhere here. Mhm. Okay, it seems that it will work as well. Yeah, I'm finishing, sorry. Yeah, so we have this nice dashboard here where you can take a look at the leaderboard, and you see that we have this Yelp agent that we created and the OpenAI chat itself. And so we have the answer relevance, the ground truth relevance, and as you can see, it is a little bit better in Yelp agent, but still not very good. And it's quite low in OpenAI agent. So if you are asking the pure OpenAI model about something like tell me the best place to eat, it will not answer you correctly. And the cool thing here is in that you can go inside of it, inside of every answer, and take a look at the details about how it's about how it was asked, about the responses, how it was measured, and so on. So basically, like there is a lot of tools like this. I think that you can explore it, and if you are using agents somewhere, especially with the regs, it may be very helpful for you. So probably, yeah, we are running out of time, and probably that's it from my side. I will share everything with you, what we've been looking at today. But if you have any questions, feel free to ask. Yeah. Sorry about what? Yes. I don't think so, actually. Because when we are using different models, we are using different even different number of dimensions to represent our data, and so it will depend on the model, I would say. Okay. I would say that probably yes, we can, but I don't think that it is like will be very very relevant to measure it, because it's much more easier to get the other model and try to get the other representation. Thank you.